next talk, so we don't have the roundtable. We have the pleasure to have Arnault Ioualalen. So Arnaud, you have 2 masters in computer science and mathematics, and you also did a PhD in computer science. After your PhD, you focused a little bit on teaching and research, and then you built the Numalis company in 2015. So the Numalis company is specialized in the robustness and explainability of AI models based on formal methods, so best topics ever of today. And as part of Numalis, you are also expert in the ISO SC42 and editor of standardization and documents. Apart from that, you're also involved in the project called MLIP with the certification authorities of aeronautics, so EASA, to ensure, for example, of how formal methods and Numalis activities can be a mean of compliance for the certification of AI models inside aircraft. Thank you, Arnaud, to be here today, and looking forward to your talk. It could be either in English or in French, as it pleases you. Thank you.
All right. Hi, everyone. So I wasn't sure if the talk would be in French or in English, so it will be both. So slide will be in French, and I'll speak in English, so that everyone can follow. So let me maybe share screen. All right. So is this working? I don't have any feedback. Yeah, it's working?
Yeah, for us it's great.
All right, great. All right, okay, so hi everyone. So I'm Arnault Ioualalen, I'm the CEO of Numalis. So sorry not to be here. I was already tied to an event in the European Space Agency today, and they asked me to fill in for the missing roundtable. And so I'll try to give you a quick heads up about what we do at Numalis, which is at the intersection between formal methods, neural network, and standardization. And so let's right in. So right now, everyone told about us that everyone told that AI will be like everywhere, and it will be like a great world. Everything will be fine, and everything will be perfect. However, from my experience, when I'm working with the industry, the AI I see is rather this one. So everyone is talking about it, but no one has seen it. And so for now, the reason why this AI is not really already up to speed in the industry is because about trust, because it's hard to trust this technology right now and to deploy it in real scenarios in critical industries, for example. And no one to want to be the first to have its own system blow up in the face and have to deal with the public fallout in terms of PR. And so this is why we need some form of either regulation, standardization, control, verification, whatever you want to call it. We need something. And so since AI is bound to be a huge market, everyone wants a piece of it. And everyone wants to have its own way to put trust within this system. And so you have several initiatives running in parallel. So you have at the low level internally in industry, you have, for example, like ethical charts, or you have label popping up. You have obviously now a standardization efforts that has been done both at the sectorial level, for example, in the aeronautic or in the automotive, or at the more general level, like the ISO, IEEE, or CENELEC. And above of it, you have all the regulation that is also starting to pop up, both at the national level, for example, with Singapore or the US or Canada, and at the international level, for example, at the EU level, which has its own regulation brewing called the AI Act. And I will talk a little bit obviously of that, because it will be the main driver of the certification in AI system, for example, in Europe. So the AI Act is basically a regulation telling you that if you're doing a high-risk system, you will have to comply to a lot of requirements, follow some standards, and to assess conformity in order to see whether or not you could put your system on the market. And the system concerns are obviously the high-risk system like planes, like cars, like, I don't know, medical devices or stuff like that. But it's not limited to that. It also concerns, for example, everything regarding employment, or even everything that can touch the foundation of our democracy. So at some point, marketing and publicity, or even social media might have some obligation there. So the high risk category is what is the most important, because the others are basically either it's prohibited and you don't have, and you're not allowed to do it in Europe, or you just have to say that it's an AI system that you're talking to, and so it's only limited risk, and the rest is, you know, you don't have any obligation at all. So how are you going to comply to this regulation, which is basically said that your system has to be like robust, transparent, respect privacy, explainable, etc. They have a whole list of terms, but they don't define most of it, and they don't tell you either how you're going to do it in practice. So when you do high risk system in real life right now, you usually follow some form of these schematic. So this is from the aeronautic industry. So for example, when you design a safety critical system for a plane, you can build it, you know, on paper or using some software to design it and to verify, first of all, that the design corresponds to your need. And then you have the whole process with the V cycle, which enforce quality and assurance on the software you're building. Then you have to put it on some hardware and verify that the integration is working on, and then you can put it on your plane or on another system. Problem is, this cycle here doesn't work for AI, because we don't develop AI system the way we developed software. We develop AI system and machine learning system, more specifically using data instead of using requirements. And that's the whole point here, is because, for example, if we want to have a life cycle of an AI system, and here is an example taken from the ISO 22989, you have different steps you want to verify, and across these steps you have some activities you have to enforce, and each of these activities are implemented in rather different fashion than the one that you do when you're just designing classical software. And so we need guidance in order to see at each step how we're going to operate and how we're going to process all of that. So for example, if you want to do some validation, so usually when you want to validate, you're doing some cross-validation. So you have your data, you have some training sets that you extract from, and then you're going to validate on the rest. Problem is, you're not really aware of all the data there is, because you're maybe in an open world, and so you have n dimension. It's not easy to represent, and you don't really know the distribution of all of that. And so you might miss some vulnerabilities. You might miss some places where the system has an unsafe behavior, where your system is not operating the way you want, and you want to correct that. So here, formal methods can be a nice complement to the rest of the statistical analysis that draw statistical, sample. And what you want is to explore beyond the data and try to fill in the missing parts, the points that you don't have, but that might occur. And so here is the core idea that behind it, formal methods can help cover more grounds, explore a little bit farther than statistical one. So that's basically the dichotomy between the two. All right, so here I'm going to skip it a little bit faster, because I heard that colleagues from Zurich has clearly explained what abstract interpretation is. So basically, you have a non-tractable function. You don't know what shape it has when you experiment on all of it, and so what you do, you make an abstraction of it in order to see in a tractable way whether or not its specification falls within the safe bounds or not. So I'm going to fast travel here. All right, so once you know what's abstract interpretation, is you want to apply it to maybe a neural network processing images. And so here, what you start to realize that, okay, for example, I want to detect whether or not there is a particular adversarial example around it. So I want to have a nice bubble where I know my system is safe, and I want to verify how much this bubble can grow before having some problem in terms of system behavior. And so you can grow and grow the bubble in order to see whether or not the specification is still holding, that your system is still telling you that this is a plane. And so the more the bubble is growing, obviously, the more the images that you're containing are distorted, are changing, and so you might have at the end images that doesn't really look like at the beginning. Interestingly, what you can do is you can do, for example, a space that contains not all images around it, but some that are of interest. And so you can define your own way of defining the neighborhood in terms of noise. And so, for example, here, this is from a project we've done to the ESR. So since they allow me to use their open space to participate, I have to plug the work we've done for them. This is the kind of work we've done with them. It's to model radiation that affects sensor, or flare that affect the sensor of the Rosetta spacecraft. And so they want to verify whether or not the system, the AI system processing this kind of picture, can resist to this particular perturbation, and not just perturbation that are random around these images. And so we've done a nice modeling, mathematical modeling of that, and then we define the abstract object that allow to verify whether or not the system is holding in terms of performance. But you can do that obviously on pictures, but you can also do it on time series, for example. So you can, for example, take your time series, decompose it in a way like using tendency, seasonality, and noise, and add a specific noise to the seasonality, the tendency, and reconstruct your signal like that, and build all the neighbors of your time series, giving a specific noise you have in mind that represents something in your world that makes sense. And so doing that from one time series, you can explore several, and you can explore all the behavior the system can maybe have, like if it's predicting something from a time series, is my prediction going above a certain threshold or not? And so you can have a sense of how much the system will stay stable and will continue to have a good performance depending on the noise you're considering. Growing the bubble also allow you to verify how much the system is changing over time. And so, for example, here what we see is that we are increasing gradually the size of the bubble. And what we see is that the classification that was really high score at the first is going to be challenged by some other classes. Here, the red one. And so you can see that your system might confuse the blue classification with the red classification early on before getting confused with others. And this gives you hints about how your system might be improved, maybe in changing the dataset. And so formal methods here also can give you some hints about how to improve and how to monitor the performance of your system. So I've talked a lot about like robustness and stability, but you can also do some interpretability. And so here is also the work we've done with the ESA. So trying to build an abstract object and extract an analysis of the interpretation of the decision. And so what parts are more used in the abstract space in order to build interpretability framework of this object. So it's also something that can be done using formal methods. And so here is an example also from our tool. So here we analyze pictures of planes, and we can filter to analyze what are the most important pixels regarding the space we are covering. Here, the important part is that basically clouds are not used. And so this is a good thing, because I don't want my system to learn that clouds imply planes, because that would be bias. And so I can verify stuff like that and have a good process of verifying that way. So all of that is basically the ground ideas that was implemented in the standardization framework that we define at the ISO. So you recognize on the right the life cycle that is proposed by the ISO, and so at each step of the life cycle, we as an expert community try to define what kind of meaningful requirements can we have, and trying to put it on its standards in order for later on have maybe a regulation using these standards in order to build certification framework, for example. And so, for example, at the inception level, you have to define some form of what is your domain of operation, what kind of perturbation your system can have. And so it has radiation, it can have flares, it can have blur, it can have something. And so you can have a description there giving to the system engineer the necessary requirements that he has to comply. And so here you can have in the ESA concept paper and also the MLib project a lot of interesting ideas that that are publicly available and that I encourage you to go read in order to get a sense about how we can do that. Then on the following steps, so when you design your system, you validate it, and you deploy it, you have different requirements that can occur. So, for example, during the design, you want to verify the characteristic that your system has learned. So here you go back to the interpretability of system and explainability of your system. You might want to check also the separation of your class. So are my classes separate enough in order to be stable enough? And so you can then compare different versions of your AI system and choose the best one. So here you can see how the formal methods can also help you there. During the validation and verification, basically you want to explore the domain of use. So you want to cover as much ground as you can in order to enforce that your system works. But you can also verify what are the meaningful perturbation you need to be robust against, and how much you are robust to it. And so here you can see that we can measure different perturbation metrics and have results there using formal methods. You can, for example, for the exploration of the domain, there are a lot of techniques, for example, to project on a two-dimensional scale the actual training set you have, for example, and trying to measure the robustness on this space. So this is kind of the work we've done in Numalis. So trying to see how the robustness space is evolving over the input space. And on perturbation, you can measure for specific noise how much your system is still robust or not. And for example, in this example for radiation, we can even have robustness proof up to like the maximum amount of noise of 255. So basically anything between a dark or a white pixel. I'm going to move a little bit forward for that. So here's for perturbation, for radiation, for flares. So for flares, robustness is way below. We can prove like until plus or minus 10 on each pixel, but for radiation we can prove until 250. So once you've done that, you're supposed to have validate and verify your system. Now you have to deploy it. And so here you're starting to have maybe problems because you want to move towards an FPGA or some, I don't know, fancy hardware that's going up to space or that has really limited capacity. And so adapting the AI to that will cause some problem. And so here again, you have some requirements in order to guarantee that your system will not drop too much in terms of performance. And finally, once your system is up and running, some requirements can occur that you have to verify real time that you're not being under attack, for example, by adversarials. or that your system is still operating within the bounds of its domain of use that it was intended for. And so here there is a lot of work to be done still in R&D, I guess. But there are maybe solutions using formal methods or others in order to verify that. So I've been really quick, I know, but I'll try to keep it on schedule. So everything I've talked to you is what we've done. We've tried to develop and done it at Numalis with a tool called Sample. Here you have some links there if you want to play with it. We have a freemium account available. You can go there, register, and play with it. Please do. That will be great. But basically, we want to take all of these ideas from the ISO standards necessary for the certification to be implemented in tools that can be plugged in within your own framework of development. So that's the goal we're aiming for. So I still have like maybe 2 or 3 minutes. So just to give you a heads up about standardization for those who are interested. There is one committee called the ISO subcommittee on AI, the 42, which regroup a lot of the international experts, like 300 of them, and with tons of projects going on. And so I'm going to give you just a quick heads up on what's the most, I guess, important project you should be aware of. Note that all of these projects are currently being almost copy-paste in the European framework for the future AI Act. And so everything that is done in the ISO is probably gonna end up in the implementation of the AI Act. So that's the way you should be looking at. So, for example, in the working group 1, you have already 2 terminology standards that are published, which are really helpful to define the concepts and have a common terminology across the board. But you have also the management system of AI that is almost published and would be the basis for the future certification. So the 42001 will be the document to read if you're ever to be impacted by certification of AI. In working group 2, if you like data, you have tons of documents there regarding data management, data bias, etc. And so you can really learn a lot here. Not much yet to be published, but it's underway, so it should be there in like a year or 2. Working group 3, a lot is going on there. A lot is already published. It's the one that deals with trustworthiness. So it's really the foundational work in order to have trustworthy AI. And so here is it's where our documents driven by Numalis regarding robustness of neural network are being published. And so you have a lot of to read there, for example, on risk management, on quality model for AI system, for robustness, etc. And so here you have tons of reading if you want. And one also that needs to be looked at is the working group 5, driven by China, because they are pushing also their own standards there. And you might be aware that the US and China has a really intense competition regarding AI right now. All right, I'm right on time. I hope it wasn't too fast. I hope that you still managed to grasp some information using regarding formal methods and what we do at Numalis. And if you want to know more, please go to sample.com and play around with the tool. It's free.
Je vais le faire en français. Je sais que dans le cadre de Rocaille, ils essayent de transformer le cycle de V en W. Je veux savoir si vous pensez que ça allait résoudre le problème ou s'il allait toujours avoir des problèmes de traçabilité, par exemple.
Alors le cycle en W, oui, je le vois très bien. C'est ce qu'on fait un peu dans le milieu avec MLIP, justement. Je pense que c'est une bonne base de réflexion. Je pense que ça résout pas forcément tous les problèmes. Mais en tout cas, c'est un premier pas. Et sorry, I forgot I forgot to respond to you in English. Yeah, so I think it's a first step, a good one, maybe not a perfect one, but it brings interesting ideas, and also it brings the notion that you can go back. It's not a straightforward, process. You have tons of back arrows that allows you to iterate and modify your design, modify your training set, etc. And so this I think is the good idea to get from this cycle.
Okay, Giant is nice enough, so I can start. Thank you for this presentation. It was really interesting. I have two questions. Among Airbus colleagues, one of the drawbacks we have with formal method is that we are verifying the robustness of the model we have on our computer, but at the end it will not be the one that it will be embedded. So is Numalis looking into all the quantizations or all the embedded process inside this framework?
Yes, totally. This is still R&D, and not to put someone under the bus, but I think someone from my team is working on that and is present in the room. So yeah, we're looking to for techniques where giving a specific objective of maximum deviation you want to tolerate, we want to infer what is the minimum fixed point arithmetic you need in order to enforce that using formal method. So yes, definitely we work on that, and we hope to have something real soon to propose within the tool.
Thank you. And the second part of the question, it's similar. It's once the AI model will be embedded, we will have other kind of adversarial attacks which is more linked to the hardware, like bit flipping or something like this, which is not really tackled in the machine learning field. Are you also using formal methods, for example, to take into account, or more considering that you will have some redundancy in the weights to check that it's not corrupted?
So I guess the answer can be in two parts. So first, you might want to model this perturbation as another perturbation that to be robust against, and so have a system that can resist to that. But the other answer is I think if you're in a critical system that can have this kind of bit flipping, like due to radiation, for example, yeah, redundancy would be the right answer to have like a voter system and compare results.
Thank you.
Thank you, Arnaud, and thank you, Melanie. I still have my question. Yes, so with the formal verification, then and formal methods, you need the properties you want to verify. Is there work inside the different groups you are participating with to think about how to do the knowledge management for these properties, how to make sure that we have taken into account the right properties to really show the robustness of the model? Because it's not always easy to define these properties. So is there work on that?
Yes, so that ties back to the discussion about the domain of operation. So meaningful properties has to be derived from a meaningful domain of operation. Otherwise, obviously, you're not proving much. And this is a hard task. I agree, and there are work both at the ISO but also at the EASA. For example, you have a good document was published. I think it was for the FAA, where the team used a description of their domain in a very, very formal way, and their domain was, I want to land a plane on a runway. So it's really open world, but they approached it as really a mathematical problem, that my plane has a certain angle. This angle should be between this and that. The runway has a certain distance, a certain color, and etc. And so they're trying to really describe their domain in a very formal way, so that they can derive meaningful requirements of performance of the system. So I think this is a way to build something that is useful and that can be convincing, obviously, for the certification, ultimately, that has to read this document.
Yeah, so I can comment your answer. So I agree with you for the input domain, but especially for this case, for instance, and Melanie showed that in her introduction, that we are also interested in properties on the model itself, on the behavior of the model, for instance, like monotonicity of the model that we expect on certain variables, which is not really part of the input domain, but more on the behavior of the model that we expect.
Yes, true. The interpretability is also part of the requirements you want on your model. You want your model to respond in a certain way using certain part of the inputs, for example, to not have a biased response. So yeah, there are requirements that you can derive from the input, and you have requirements that you can express on the model itself. It's true, yeah.
Thanks.
Arnaud, Gregory speaking. I have one question regarding the scalability of your approaches. Can you say a few words about the size of the networks you are able to deal with?
Yeah, so basically we want to deal with industrial grade neural network, but also we are currently processing also support vector machines. Right now we are able to even analyze architectures like tiny YOLO, so detectors. So with I don't know how many millions of parameters, but I think it's tens of millions. We can analyze architectures of classification of pictures like VGG 16 or VGG 19, sorry. So we are focusing on that. We are focusing on having real world grade industrial neural network, even if it's not easy, but we cannot just analyze NIST or CIFAR dense neural network. That's not enough.
Okay, thank you. Any more questions? No more questions. So thank you very much, Arnaud, for being virtually with us. It was very nice. Thank you very much.
Thank you very much.